How's everyone going? It's Matthew Coles, and we've got Aaron here as well, and Paul from Devs in the Sheds. We're not in the sheds today. We're actually over at Paul's house outside
Outside
the
the
shed.
shed.
It is a little windy, it is a little rainy looking, so wish us luck on the stream. Hopefully the video signal's okay as well. There might be a little bit of lag, so I'll apologise in advance. What is the plan today, guys?
Well, we've talked about it a couple of times, and we've done some work with the Arduino and Raspberry Pi and so forth. This week we have decided to, get something up and running on the Raspberry Pi Pico, and we'll talk about and introduce that device later. But we're going to power it by a little. It's called a BioLite. Is the brand of this device, and it's a little container. We'll bring it up. Maybe Matt, you can bring it up now. We can
Yeah,
sort of show you what it
let
looks
me
like.
add it in for people, and I'll
So
make us tiny. There we go.
So this is this little BioLite camping stove kind of little device, and basically like the silver bit that you see at the back, it's kind of like a little, looks like a top loading washing machine, I guess is what you would say. It's got some sort of holes inside of it. The orange piece that you're looking at inside of that has like a battery. That battery operates a little fan, so that top little like vent thing that you see there is, it'll suck air in there and it'll blow air into that sort of washing machine sort of thing. The idea is you light a fire inside that, like, effectively like washing machine barrel. The fan blows air onto that fire to keep it like, nice and hot and burning like really well. And at the top of the device, inside there is a little heat exchange unit. That heat exchange unit will take the heat that's being produced by the fire, convert that back into electricity, will charge the battery that runs the fan, but additionally it'll provide enough power that you can run a small USB device. So you can, recharge your phone, for example, or in today's instance, run the Raspberry Pi Pico. So the USB cable that you're seeing at the bottom plugged in runs, along the desk onto our Raspberry Pi Pico, which we've set up and plugged into one of the little breadboards here. So we will be writing some code, deploying it onto the Raspberry Pi Pico, but powering the Pico by fire. So that's kind of the plan today. We've stitched together a few things. It should be fun. It can be a little finicky sometimes starting the fire, so hopefully that works okay. But yeah, it should be kind of fun today. That's why we did it outside. We didn't want to get smoked out inside a little room. So yeah, we're just outside the shed, and Dev's outside the shed today.
Perfect. So hopefully everyone's going to be pretty excited for this one. I know, Paul, you've wanted to do this for a while. Before we get into it, though, Aaron's going to be our coder today as well. Is that right? You've made some basic app to basically say hello world through LEDs just to start.
Kind of the standard hardware hello world is always a blinking LED.
Yep.
So that's what we're going to do today to start with.
Cool. I was going to share one particular AWS announcement before we kind of get stuck into it. This is a really cool one. As everyone knows, I'm quite passionate about, let me see, yep, it's on the screen. Quite passionate about Amplify, and I really, really do like Flutter and Dart as a language. So we spend quite a bit of our time with front ends, helping customers as well, not just back end and IoT projects within Devs in the Shed. This one happened to drop overnight, and it's effectively, AWS Amplify's had support for Flutter for a fairly long while actually on mobile. But Flutter's now multi-platform, and so what the Flutter team has been doing at AWS with AWS Amplify is effectively working on web and desktop support. So this is kind of like the first piece to getting Amplify to now work across web and desktop use cases for Flutter. So I'm going to definitely be mucking around with this in the next couple of weeks. We do have one of the product managers interested in kind of showing everyone in a few weeks all the stuff that they're working on, hands-on, some of the example projects as well. So that will be really interesting. And so just one quick announcement today. So I'll stop my screen share, conserve some bandwidth considering we're outside in the Australian outback.
Yeah, we've got Wi-Fi and cables running all over the place on a little card table, and sort of I would say like a homebrew setup. Definitely.
Yeah.
I have one very important one I think that everyone is probably keen to hear, and that is because you guys have hassled me from the very beginning of Devs in the Shed on running a Windows machine. So today you'll see my code running on an M1 Mac. So just I do have the M1 and it is up and running.
Yeah, there's nothing wrong with Windows laptops. Aaron's done a lot of work on C#. Paul's done a ton of stuff in C#. I think I did like a little bit back in the day with game engines. The Windows laptops are fantastic, but we do hassle Aaron, considering a number of the projects that we work with tends to require Unix or Linux to run best.
Yep.
So
there's one more thing. So last week we
Yeah.
also talked about the M5 stack, and we had a few extra people, and thanks for that, subscribe to the channel. And we said, if anybody had some ideas of what we should build in the future on the M5 stack, submit those ideas. We only really had one submission, so that was Brett Cooper. So Brett will comment back onto the YouTube channel, but if you're out there, like, reach out to us, connect with us on LinkedIn or something, and we'll get out to you that M5 stack, so we'll send that out. So yeah, congratulations on winning that. There's some interesting things there. We'll look at implementing one of those specific suggestions you had on the M5 stack when we build that up. So yeah, thanks for that, Brett.
maybe we could do something with the Pico this week as well.
Yeah.
So just looking at who's come into the chat, East Coast, welcome. Kia ora to fellow New Zealanders.
Yep.
How do we want to start this off? Like, what do we want to look at first? Do you want to? Shall we start with fire?
I think the first thing is I probably got to start this fire, right? Because it takes a little bit of time to get it warmed up. So
Yep.
we'll see how we go. I've got a
When we get the fire started, then we might run through the code before we actually turn it on and show what's
Yeah,
running.
that's good. Yep.
Because then if we want to, we can make changes to it and stuff, but we'd have to unplug it from the fire. So as long as we can see what the code is that we're running, but we'll actually see the actual, when we bring up the Pico cam, we'll actually see that it's running on the fire.
Yeah, so I've got a little, if you can hear me, hopefully.
Gonna add
There's a
the
little
Pico cam?
a fire lighter in there. You can see now that
I'll do it in a second.
Yeah.
the fire has been ignited. That fire lighter will sort of just keep it going. Then the sticks and the little bits of wood that I've got in there will keep it going.
Actually,
Sort of watch
bring up
it.
the-
I'll
the
keep
LED.
getting up and down and poking at that fire.
Yeah.
But you can see now that the fire is up and running. The fire is charging the battery. But sort of tilt this a little bit.
Yeah, Paul's just moving it just
we
to fill in
see-
the audio gaps.
Yeah, if we see the left side of the BioLite temperature fire burner, there is there's three lights. So there's one, the green, which is the battery level of the battery inside there. We'll see that lift and charge as the fire heats up and starts making temperature. The middle bar, which you can see those lights, is the speed of the fan. So the speed of the fan will effectively determine how hot we can get the device. And then at the end, there'll be the actual temperature of the fire. So we want to see that temperature lift up over time. And
So the temperature, will go up. Paul's just increasing the fan speed to push the temperature up as well.
yeah, so
to get it started.
Yeah, getting it started can be like a little finicky. We'll sort of have to fiddle around with it a bit until the wood sort of catches on fire and we get a bit of heat in there. So I'll be sort of up and down through the stream, making sure that the fire keeps going. Once it's established and it's going, it should be fine.
Yep, nice. How did we find out about these originally? I feel like it was at camping. One of the other AWS members,
Yeah.
like a year or two ago, used it to make coffee for everyone while we're camping. Is that right?
So yeah, there was another AWS member that we went away on a camping trip, and he was like keen on camping. He had some points, reward points from an old organisation he worked at, and this was one of the devices that he purchased and brought that along, and we were using that as a little night light because we had a little USB light plugged into it that was powering it. You can see that whilst I'm using just the fire to create electricity here, and I don't have the pieces here. If anybody's interested, I can show you those pieces. But there's extra pieces that sit on top, so you can use it as an actual grill, so you can cook meat and cook food on it. So I've done that before, and it's pretty fun. It's like nice and little and portable. You can take it out, make a fire. But it's also got like a jug that sits perfectly on top of that. And so you can heat up water, you can make 2-minute noodles, you can make your coffee in there as well. So yes, we went along, we heated up water, we made coffee on it, as well as powered some of our USB devices. I think we were charging phones at the time. And that's where we sort of conceived this idea that maybe we should, power something on the internet with this device.
Yeah, make coffee, power things at the same time. I can see that the orange light on the left-hand side's actually come on, so it is starting to heat up.
Yeah.
Yep.
So Paul's just adding more to the fire. Mookie Monkey, exactly. Fire.
Fire.
If anyone gets that in joke. So, yeah, that's it. So that's going to be burning away for a few minutes. We thought we'd get that started. Now, I know, Aaron, you wanted to have a look at the Pico Cam. I think you've got the app running, so let's have a quick look.
You can see, as I said, like the hello world of hardware is generally, let's make a little LED blink. You can see on the very left-hand side, sort of down the bottom on the left-hand side, there's a green LED. That's the onboard LED for the Pico, and that's essentially pin 25. But just to show you that it's not all smoke and mirrors and that we are actually programming hardware and we're not just relying on
there's my
hardware.
hand to prove it.
I have added a red LED. That's the one on the very right hand side. So the red LED is running obviously through, at this stage it's running through pin 16 and from pin 16 through to ground, and then I'm also running through a, what do you call it, actually that's backwards, so I'm probably going to burn out the LED, but that should actually be running through a resistor as well, so it's not taking
I've got like a pack of 100.
not taking the full force of the 3 volts. So I'll need to change that because we're just running the LED out to the ground through the resistor, so that's actually going to burn the LED out eventually. But what we're seeing here is obviously an infinite loop. So you can see on the very left hand side it's plugged into the USB. That USB is on a long cable over to the fire, and so we're actually running this 3 volts into the Pico from the little battery that's.
Is it
being
Pico or
powered.
is it Pico?
Pico?
I think it's Pico.
Yeah.
I don't know. I'm just like, I've never heard Pico. I'm like, maybe I've always been wrong.
It's a Raspberry Pi.
Pico,
And
yeah, I don't know.
P-I-C-O, I don't know.
Maybe.
Pico, I'm not sure. I'm used to PIC controllers, so I would usually say PIC, but I thought it was a Raspberry Pi, so it's a Pico. Anyway, irrelevant.
So, like, at the moment, Aaron, we've got the Pico connected to the battery source. So it's just simply connected to the power source. We can see the flames are coming up, and if you sort of look
there we
closely,
go. Look at that.
on the left, you can see that temperature is starting to rise up, so it looks like it's doing its job. But the battery or the fire is powering the Pico. So I guess we'll take us all the way through that, but once we write the code for the Pico, we are not connected to the Pico device the same
Correct.
way we were in the past when we would SSH directly into the Raspberry Pi.
Yep.
In this instance, we are like writing the code, then we deploy that code onto the Pico. So we can probably go through that as well.
So right now, exactly what Paul said, the actual Pico is running. So when we run hardware, it runs through a loop. That loop is actually running what we've set in the main Pi. So there's a main.py which gets called every time it runs through the loop. That main Pi we'll go through in a second is just importing the pinouts that we need to run the physical hardware, so the GPIO ports. And also a timer so that we can calculate how long it's been since the last time we toggled the LED on or off. You ought to maybe, let's jump into the code and I'll show you exactly what we're talking about.
I'll bring it up on the screen.
Cool.
And I might just take off the Pico, but we'll leave the flame for everyone on the watch. Sure. And we are welcome for flame jokes according to SRP and KJ, just looking at the channel.
Fire.
So try your best to make flame jokes somehow.
So you'll notice the first thing that I've done in the main.py is import from the machine. So we actually want to use, so we're actually using MicroPi. So it's a Pi version specifically designed for hardware or for controllers. So we're importing from machine. We want to get pin and we want to get timer. So the pin library understands which are the pinouts for.
But can you zoom in a little bit?
Pi, yeah.
Aaron, it's a little hard to see.
How do I zoom in?
Yeah, with this Thonny. So Thonny is the IDE suggested.
Go Command Plus, see if that works.
Just increase font size.
Yep.
Which would
Do that a couple of times.
Command.
It's usually Command Plus.
It's not doing anything.
Is it Command Shift Plus? Maybe just
Might be
this
Command
app.
Shift Plus. Yeah.
Yeah, it is.
Command Shift Plus. There we go.
It
Cool.
won't be a joke when the LED burns out without the resistor.
Yeah.
It'll be very fitting if the LED actually burns out. We can chuck it in the fire and burn it.
Yeah, I've got a whole pack of LEDs, so we can swap it out and actually add the resistor to the actual pin voltage.
Do you guys know how much tech costs these days? Like a resistor's like $50 now.
It's expensive now with the price of everything else. So you can see I'm doing an import from machine, so that's pulling in the library to understand the pinouts and to understand the timer. So the timer actually comes from, it's a library that understands the cycle in the hardware. So every time the cycle, we call it a tick, every time the hardware ticks, it can actually count how many ticks have been, and it can actually break it out and understand what's seconds, what's milliseconds, what's minutes, and that side. So we can actually set up a timer that it won't actually call execution of what we put into our Python every time it ticks. Otherwise, you wouldn't actually see the LED going on and off. Even if we were toggling the LED on and off and we weren't using the timer, it would just look like it's on, because it's going on and off so fast that it's actually just looks like it's always on. So that's why we use the timer. So the next two lines, lines 3 and 4, are just basically creating variables for our LED on pin 16 and LED on pin 25, and we're using the pin library to say we're going to use pin 16 and we're going to do pin out. So this is an output pin. These are digital pins. There are also analog pins, and that's when we can get into voltages, so we can say how much out, but at this stage we just want on or off. So the actual pin 16 will be an out pin, LED 25 will be pin 25, pin out. The difference here is if we were running a sensor and we wanted to pick up, say, a temperature sensor, if we actually had a temperature sensor over on the fire there, and we wanted to read from the temperature, we might set one of the analog pins to be pin in, and so we're reading from the pin as opposed to sending voltage out of the pin. Then line 5 is our timer, so we're just creating a variable and instantiating the timer, and then we've just defined our tick function. So what do we want to do when the timer calls back, or the function that we call back from the timer, when it gets to the seconds that we want to execute a function. And so then we're declaring our LED 16 and 25 as global variables, and then we're calling toggle. So we're basically just saying turn it on if it was on, off, turn it off if it was on from its previous state. Then you'll notice on line 12, I've got a LED value 1. So because I didn't want to just have the onboard LED and our LED that we've pinned in to pin 16 flashing at the same time, what I've done is I've just instantiated LED 16 value as on, so that when it toggles, it'll toggle off. So by default, the pins are off. So when LED 25 toggles for the first time, it'll toggle from off to on. So now they'll alternate. So we've got one on, one off, one on, one off. And then all we're doing is we're initializing our timer function with a frequency of 1.5 seconds. So every 1.5 seconds, the mode is it's a periodic timer. So we're just going on a loop. We want to call our tick function, and that's it. It's really as simple as that. I think Paul and I this morning, when we were just testing the Pico or Pico directly off of the Thonny, which is our little IDE that we're running here, you can run commands when it's plugged in. You can see down here it's the back end is terminated, it's disconnected. You can actually run direct commands to the Pico hardware from the USB, right? So this morning when we were testing, is it working, we loaded up some commands in our command line and just ran a very simple for loop. So we basically said, for X, I think 10. So we looped through 10 times. If it was odd, flash it on. If it was even, turn it off. And we just ran through that 10 times just to make sure it works. But because we're powered from a fire, obviously we don't want to just execute something from the laptop and run it onto the USB. We then upload main.py onto the board. So using the Pico, using the MicroPython, it understands when you first drop MicroPython runtime environment onto Pico, it boots up, puts itself into, it like updates the firmware to run the version of MicroPython, so that it knows when you drop the main.py into the storage, it knows to read from that as the main function, right?
Yep. So that's an important piece. Like you can have multiple files and deploy multiple files and break up your MicroPython application and deploy it onto the device. But the file it'll run by default is like main.py.
Yep.
So we need to make sure we save that as main.py. And just a little bit of a step back, when Aaron talked about the difference between analog and the digital outputs, if we were to look at that LED that was flashing on and off, that is going when we set the pin to be on, it is passing the full amount of voltage to that LED. So the LED will be getting I think it's 3.3 volts that goes across to that LED, which will turn it on. That is like a digital out, so it's either on or it's off. If it was an analog out, then we could say give it 1 volt, and for argument's sake, 1 volt would have a dimmer illumination of that LED. So that would be the difference between a digital out versus an analog out.
Yep.
For something on the Raspberry Pi.
And the opposite being a analog in, so the heat sensor, or if we had any sort of it's freezing outside the shed right now, so if we put a temperature sensor on one of the analog pins, we could read And the way that a sensor works is it's in variance of voltage, right? So you might have a maximum voltage of 3 volts and a minimum of 0, so 0 being off. So then anywhere between 0 and 3 volts will be our temperature. So basically, dependent on the sensor, you'll need to know how to program it to say, well, if I'm receiving 1.14 volts, then you need to know, based on the hardware manufacturer, so based on the sensor itself, how that translates to degrees Celsius or degrees Fahrenheit. And so then you can write your conversion from voltages to degrees Celsius or Fahrenheit based on understanding the variance from 0 to 3 volts or 0 to 5 volts, depending on the manufacturer.
And just reading the chat as well, so SRP SCO, if I've pronounced that right, again, has shown us the pronunciation through like a link that he's put in the channel on Twitch, is Pico.
It's Pico, okay.
Pico.
So it's not Pico,
so it's not Pico,
it's
we're all wrong.
Pico.
Yeah, okay.
Cool, so from now on, Pico. Yeah, so that's back to Paul's point, right? Using that main.py. When you get into some more advanced programming, obviously you'll have heard me harp on about solid programming many times throughout the series. We don't want to run, like, when you first get into programming with Python, this is the danger of learning Python from scratch or from hardware like this, and not learning object-oriented programming, is you might end up building a massive big main.py, which actually becomes very hard to manage. Then you might actually start bringing different libraries in for different functions. You might be running different sensors, different hardware that connect to different pins. You don't want to have to manage all of that through your main.py. So your main.py essentially becomes, if you're used to working with games engines, or if you're working with other controllers like Arduino, or directly with PIC controllers, or depending if you've come from sort of pre-Python days, you'll be used to the actual main.loop. So you have your main loop inside.
Well, yeah, you have your main Pi, and then you'd have your event loop.
So
I think Python, like, it's generally best practice to do that as well.
So that's what the main Pi is now.
Yeah,
is your
but
main
what I've noticed is that, like, a number of the tutorial videos on YouTube, etc., like, lean towards having one massive file. They don't really teach about.
Yeah, so I disagree with the one main file. Just for
I think it's good for beginners.
Oh, absolutely.
But like there comes a time where it's like you might want to see like how to scale out what you're doing, right? And that's,
so you might use your main.py. So that's the entry to your loop, right? And you might have some interrupts there. So you might have some capability to have a button, so that you might have the button in the main loop, so that if it's pressed, it might do something. But that do something might be sending a signal to another file, so a sensor file, that your sensor.py or whatever you've created, that you're importing, so that you can run all of the logic that's specific for that sensor that you want to run in that sensor.
Or it might even be starting up individual threads.
Yes,
like if you think of a game engine, it could be like, let's run sound and music through like thread 1, and then thread 2, let's do game physics. And
so right here you can see that I'm running a timer, so timer.init. Everything at the moment is just calling back to that one tick, right? But if we have multiple sensors all running off this one piece of hardware, so now we've got a heat sensor, we've got sound, like a Pisa sending sound out based on, say, the voltage of the sensor in for the temperature gauge or something. We might not want to have those run on the same timer, right? So to Matt's
especially
point,
game engines,
multiple threads.
You're like, that's the whole point of having like CPUs with multiple cores.
Yes. So we can then control what's happening in different sensors or different bits of hardware on different pins in different loops. And then also, if there's an interrupt on one, you might not want the interrupt on one piece of hardware to affect everything else. But if you're running in one main loop and you have an interrupt on one piece of hardware that then creates a pause, like it basically stops the thread, then your entire solution, so whatever it is you're building, it's going to stop. It's going to pause because one piece of hardware has sent an interrupt that may be an error, and you don't want everything else to fail. You just want to sort of pull off that piece of hardware, put in a replacement and have everything keep running.
Yeah, or to get more complicated, you have threads that need to communicate to each other once something's done. Like, there might be a collision in physics, and then you need to have audio processing kick in on that particular thread with like a sound to say flunk. I don't know.
So I know, Aaron, you brought along some componentry. And we like to live code. Let's add in another couple of LEDs, or do we have will one of the little servo motors? Can we make something?
Yeah,
move?
we can.
Let's do something, and let's watch you stumble through plugging in some wires live.
So let me unplug it from the fire, so we can actually plug it into our.
So I'll do
Yep.
that.
Yeah.
Well, maybe we'll take the audience through like what we've got, like in terms of the random stuff that everyone's bought today for their different picos.
Yeah.
Yeah.
But also, like, while Aaron's plugging that in, Matt, bring up the BioLite, and we'll be able to see now, as I sort of mentioned earlier, if you make it like
The big one.
big one, as you can see now, the battery itself is almost fully charged. It's blinking to the top. The fan, I've left that fan the same temperature, but you can see on the far right that orange light, and I'll sort of point to that. So here, that has increased in heat. So now we've got like a good amount of heat at the top at that heat exchange unit, and we're generating plenty of power that enables us to run the Pico. But it would it'd charge a phone. If you put a little USB hub, it could run a couple of small devices, but also is running that fan at the same time. So, but now I've disconnected the USB from just running the battery. We'll plug that all the way back directly into Aaron's machine. We'll write some code, we'll run it on the Pico, then we'll save it on the main.py, which will effectively deploy it to the device. We'll disconnect it from Aaron's computer, we'll plug it back into the battery, and we'll watch the new setup go up and running.
And someone's saying the BioLite idea is pretty cool. Energy from fire I can see on chat. I was actually going to say, like, we're almost completely off the grid here, right? Because the power coming from the power coming to the Pico is obviously through the BioLite, but the internet as well is through Starlink, isn't it?
My internet's powered through Starlink, so we don't have any like physical connections.
I'm just
it was very stormy last night, and Aaron and I were wondering, hopefully we've got like actually electricity today, but I do have a generator, so I could be completely off grid if we needed to be.
So you'll notice I just swapped around some hardware. So I'll just tell you what I've done. We've pulled out yellow here, or the one that's just off camera.
Actually, yeah.
This guy here, just off camera, is our 3 volts. And so you can see that I've swapped around. The 3 volts is now running down to.
Yeah,
the 3 volts is now running down to our pin 30, or our breakout 30, and the breakout 30 is on the same line now on H as our resistor. So the resistor is now connected to the LED on breakout 25. The power is running from the little yellow, from breakout 20, which is our pin 16, through to the resistor, through to the LED, and through from the LED is going back through the white line out to the ground. So up here on pin 3, that's our ground. So we know that it's working properly now, because the LED isn't super bright anymore. It's actually a little bit, well, to you it might look the same. To me, I can see that the LED is not super bright, so it's not going to burn out. It's actually being resisted, or there's resistance running through the resistor now from the 3 volts.
Yep. And for anybody that is new to any sort of like fooling with electronics, if you have one like in your hand or somewhere in that little container, Aaron, like show at the length the length of the legs of the LED. So I think Aaron's just going to quickly jump off, but you'll see that like when you have the LED, which actually, you know what it stands for, Matt?
Light emitting diode.
Yep. So it's a light emitting diode. The polarity is important. So the polarity means like, do we connect, the positive versus the negative? Which side of the pins that works? So if you have like a typical light globe that you had, an older style light globe, or a headlight for a car, for example, it doesn't matter which way you put the positive or negative, it'll illuminate and light that globe up. With an LED, it won't. So maybe hold that in front of the little cam.
Oh yeah.
Yeah, little cam's probably better.
So that comes up, you can sort of see, like it's a little out of focus, but you can see one leg is longer than the other. Oh, there we go.
Yeah.
So you can see that one leg is longer than the other. So we want the short leg to go to ground, and a long leg to go to where we're putting out the high.
Yeah.
So that's
So
really
the long leg is
there.
positive, or the power, and the short leg is our ground. So it's flowing through.
Yep. So you've got the servo motor there, Aaron.
I do have a servo.
Maybe we try and like get the servo motor to rotate, and that's what we'll try and work through in the last half of the show. We've got enough wires to sit that together, and what a servo motor is implemented for, and what you use it for is, if we think of an electric motor, typically with an electric motor, that'll be something that's like, for argument's sake, running a fan, or if you've got an electric powered vehicle, that'll run like the motor that is turning the wheels. If you've got a drill, that's what's turning the drill. A servo motor is effectively the same thing, but really we only use it to like turn, I guess what I'd say, like a little bit. So we use that motor to turn just a little bit. So a servo motor might be used for a remote control car to control how like left or how right the front wheels are turning. So it's only going to turn like a little bit one way or the other. And so usually that's, you know, often geared down. So I think that this specific servo motor has got some very low gearing, which says the motor might be spinning fast, or the tiny little motor might be spinning fast, but it will reduce what the turn effect at the end, so that it only moves a little bit either way. So it's sort of, I guess I would say it has more like torque at the end, so it can, you know, it can move, you know, only a little bit, but it's got quite a lot of strength to move that little bit. And a servo motor would be different from a stepper motor, because a stepper motor would be used for maybe like a 3D printer. So a 3D printer is a good example of where a stepper motor will be used. So it says, I only want to rotate like 15 times to the left, and it will be very precise and controlled with the amount of turns it will do. Whereas electric motor will just, you put voltage to it and it just spins really fast.
Ground and variance.
Yeah.
It's been a while since I used servos, so we might have to guesstimate a bit. But if we say,
and the other thing is looking at it, looking at the chat. I think I did see this one thing. Yeah, Tucker, I really like your idea. So how about a tiny desk fan that turns on when the temperature gets too high?
Yeah.
So this would be like a future thing, right? But that's actually a pretty good idea for like a project, especially when we get out of the cold season in Australia and we go to our summer. For those that don't know, Australia's summer is around the December-January period, so it's like quite different to most of the rest of the world.
Yep.
New Zealand's in the same camp, whereas most people have a snowy Christmas. We have a nice hot shrimp on the barbecue with fire Christmases. There we go. I fit the fire thing in. Yeah.
I wasn't looking after the fire quite properly, and it's all like going down a little bit because I wasn't paying attention. You need to keep on it, and the sticks that I have were a little bit damp.
I think you should have put the fire like right at us. I know the smoke would have like done us in, but like it would be so warm.
Yeah, it is warm over there, and it's a little cool out here in the breeze. But we were lucky today. We had a really nice day. But yes, so like you can implement like a temperature sensor fairly easy. So I think last week we talked about the Arduino. We showed the Arduino. So I am building a little temperature sensor that I want to have a little data logger and run that outside so that I can capture the temperature as it moves through the day at certain points in the day, and then plot it long term over a period of time. So I do have that temperature sensor inside, but we would probably have to sit for a little while to work out how to get it to run on the Pico, because all the libraries that I was using for that were written in the Arduino C-like language there.
Hello on Earth's just mentioned kind of what you're looking up when I look over in the background. It's trying to work out whether the servo is going to be able to be powered by the Pi.
I think it will. I think the 3 volts will.
Yeah, it's a micro servo.
Yep.
So it was designed for low voltage.
Yeah.
What I'm actually looking at the moment though is
well, is also like which one's which for the pins. Yeah,
the pinout for. What do we got here?
There we go. We got enough heat. We got it back
Cool.
on again.
Now this is just like the first release of the Picos as well. So Picos.
Yeah.
I'll get it right eventually.
Earlier
Pico.
somebody had a comment and they had the wireless
Yeah,
version
yeah.
as well.
I want the wireless version. I have 2 of the standard Picos, but the wireless ones, I've read the reviews. They seem to be a little bit shaky on the Wi-Fi. So hopefully that gets fixed with like a firmware update or something like that. But people have been using it. I think I saw a video on YouTube where someone was using it to power the commands to basically say open the garage door or turn the light on or off within the house. So it wasn't powering the garage door itself, but it was acting as the mechanism to trigger the garage door motor to basically open.
Yep.
Yeah.
So
let's have a look at what Aaron's doing, like as he investigates the ports. I always find it fascinating. Just kind of let me get the screen sharing right. There we go. You know, half the time we're in documentation as we work out how to use things, especially when you know, we haven't looked at or thought about the documentation before.
Yeah.
This motor was for your Arduino, right? Like you have
I've used those across Arduinos, like
because in theory, if we just plug those wires in, the ground and the positive either side where the LED was. In theory, that
I'd
should start
assume that
moving.
would work,
That
yeah.
Yeah, so
move
we
the
can
arm.
we can do something simple.
But we
right?
just want to
Like,
make sure that we get the right.
So if we say that's what I was looking at before. Let's
which
pull
is
up
the right wise.
the
Because
Yeah.
if we go back to Hello's comment, if we have enough power to power the servo motor. So this comes all the way back to one of our very, very first episodes when we talked about powering and driving and turning on and off like electronic devices such as like an electric motor with something like the Pico or Arduino or the Raspberry Pi, because the voltage that comes out might be 3 volts, but it's very low amount of current. So the actual power that's coming out is very, very low. So an electric motor might turn and run at 3 volts if you run it by like two AA batteries, for argument's sake. You'll have enough current or power to spin that motor. What we've done earlier to run specific pieces when we had the motor, I remember I had that little wheel.
Yeah,
I had that
yeah,
wheel,
yeah.
and
Yep.
we enabled people to turn the wheel on and off by an API. Was I had a relay in the middle. So I had the high, when the high would come through the Raspberry Pi or the Pico, the high would engage the relay would then pull in an external power source, and that external power source was putting out, I don't know, 3 amps or something like that, and 5 volts, and that 5 volts was able to easily power that. So now Aaron will, so you
I'm just pinning it out. I haven't
he's pinning it
actually.
out now. Yep.
So we want ground as well. Yeah.
So has anybody ever seen the BioLite before or played around with that? Because there's a second version of it that's more like a bit more of a fire pit device. So that produces more heat and therefore like more power. But it's a fun little device. I've used it before. It's very light. I would say like maybe 1 kilo all up. It packs up really nicely, so you can put it in your backpack. And if you're going for a hike, throw a few sausages, a couple of pieces of bread, and then you can put that in your bag and go for a hike and sit down and have like a nice warm lunch. So that's why I think it's quite useful if you're going camping. Maybe it's useful if you're an individual to make boil water or something like that.
Someone said s'mores as well, so that could be quite practical use.
Yes, s'mores.
For people that don't know what s'mores are, that's a US specific thing, I think. In Canada, it's
like a
a cracker biscuit thing.
Yeah.
I don't know if it's the right. In Australia, we have different names for biscuits, and muffins and all that stuff.
Kind of like a sweet biscuit or a cookie or whatever. And
Yeah.
then a marshmallow and then another one on top.
And there's like a layer of chocolate.
Yep.
Yeah. Yep.
So yeah, it's pretty handy, and it's actually very good at boiling water. It does it better than you expect because of the way the jug is made to sit on top of it. It keeps it really, really hot there. So that's pretty interesting. Maybe we flip back because Aaron's starting to write some code now.
Sweet. Let's have a look.
I'm just trying to figure out which is the power pin on the actual it doesn't like that.
So I think that most of the time when I've worked with this, it's a little finicky and it's a little more difficult when you're trying to do it live. So,
Well, I remember when we had a group that was streaming with us one time at a big event.
Oh yeah.
And they had their Raspberry Pi out, and they accidentally unplugged as they moved the thing towards the desk all the pins.
Yep.
And then we had like 5 minutes before the stream stressing to find out which
plugged
pins
all
were
the
used
pins.
and like examining the code against like yeah.
I know, and then we always like preaching, document your work as you move through it. So it's always difficult to think about that. And then you're putting it together because you're sort of building some sort of demo up, and then at the last minute you knock it onto the ground. Or before I took some photos,
Yeah.
and I stood on the cable and pulled it right out.
Yeah,
there,
the breadboards are excellent, but they can be
Yep.
can get you unstuck. Things can come out easily.
I noticed, Aaron, that you've got the lead stuck on. Like, what did you do there?
So it's because it's stopped running. So if I
Okay.
stop
Yep.
and rerun again, I've disconnected the device by the looks of it.
Did you knock it out or something by accident?
Looks like it.
Pin 36 3v3 out. So we're getting some hints from the audience here.
Pin 36
Six.
is 3 volt out. Yes.
Yep.
So we should be able to plug into ground and then directly into pin 36 and watch that servo motor
and then
work.
you change. Then there's the variance pin. So one is essentially the gate to say power on, power off.
Yep.
But what I'm trying to figure out now is why I'm disconnected.
Just unplug it and plug it back in, maybe.
It solves everything. Yeah, it's like
Did
the
you
default.
turn it off and on again?
Okay, so it's definitely restarted again, so it's connected now.
Yeah, it's connected again.
All right, great. So we're back in action.
So
where's ground? Plug ground.
that's what I'm
into
trying to
ground.
figure out on the actual.
Well, it's the survey.
It's the servo that I have the problem with, not
Pico.
the
Oh,
actual.
okay. Well, I mean, surely that's. Oh, yeah.
So
'cause
I'm
those
thinking
colours
brown
aren't-
is ground, red is power, and then orange is variance. So that would be, which is 33 on the breakout is. So 3 volts out is 36 on this one. So that's 1, 2, 3, 4, 5. So that's 1, 2, 3, 4, 5. Where it says 5. So that's our power out, right?
Black or
then
brown
this-
is ground.
This
is what it
should
says.
be. Yeah, brown is ground.
Yep.
So I've connected the white to the ground. So that should be 3 volts in and ground. And then I connected one pin here that's saying on and off, which actually should just be like on, off at this stage because I'm not actually doing anything except on or off. But that doesn't seem to like it. So that was pin 26. Let's change that to pin 17 and see if it likes. If it's just because I'm trying to use one of the analog pins in the wrong way.
Just take that pin and plug it into the other side of the red light.
Well, I can plug it into the actual same
Yep.
as the red light. I thought I heard it move. Let's swap around this guy and this guy. So that was pin 5 and this guy. Yeah, that
No, not working.
that broke it.
Yep.
So, and maybe to somebody's point before, they said that the 3 volts might not be enough for the.
Or do we want to see if we've got any other servos and all the other kits? We've got like a billion kits.
I'll
Yeah.
just
We could do. I could do a little LED, like a LED.
well, let's have a
screen
look
or
at these
something.
boxes while Paul goes and looks at his mega stash.
Have a look at these guys.
Let's have a see. What have we got? Resistors, none were harmed, as we mentioned before in the comments. We've got a ton more LEDs, a breadboard in this one,
What about
What
like
is
a
this?
little LED screen?
a speaker. That's
The
cool.
OLED module.
Oh,
Oh yeah, we could do that.
yeah, that's kind of cool. Oh, it's also got, these things are handy actually, like when you get kits, it gives you the resistor diagram for the color coding. It's always good. And let's just double check this Pico Dev kit as well. Let's just see what we've got in here. Actually, that's really nicely marked.
That would make it easier, wouldn't it?
Yeah. But what is this?
Do I have enough to run? That's just a breakout, right? So I
Yeah,
don't...
yeah, it's just a breakout. It just makes things a bit more easy to read.
Yep. We'll use
Touch
that.
sensor, OLED.
So I was thinking the OLED would be fun.
Yeah. We've got a color sensor. It's interesting. Another OLED. So we've got 2 OLEDs. We've got a atmospheric sensor. A buzzer. Probably a little bit too noisy for the stream. And then we've got an RGB LED as well, like a small one. Oh, we've got a motion sensor.
Let's have a look at this
And a
little
distance. So there's a few things.
OLED I've got.
Just trying to understand what this board is that they've given us as well.
So this is... What have we got? C, D, positive and negative. So that's in, out. Turn it on, off. That might be a little bit too much.
A little too complicated.
Now, yeah.
Well, that's why I did think option 1, which is like just a series of more LEDs, could be interesting.
Yep.
Yeah, I got another one. I've got a little power supply. I can bring that over, and then we can use the power.
So we can
supply
try. We can try the second servo then.
Well, that's they're the same, aren't they?
Well, in case, because it has been a while since you got your Arduino stuff out.
No, as in they're exactly the same, right?
No,
So-
but I mean, like maybe the other one shot.
Oh,
Might
yeah,
as well
could be.
just try.
Yeah, let's try that. So we've got a
We've got another idea. Using the motion sensor to detect bears. So
bear detector. Yeah.
bear detector. We don't have bears in Australia, but we could use it for possums or foxes maybe. And
Definitely we could do drop bear detection.
yeah, drop bears are a real thing. That's definitely worth a Google. If you do come to Australia, be aware
You've got to
of
be
the
aware
drop
of the drop
bears.
bears. Yeah.
So if we want external power, like I brought out a power supply, we can use external power to power the motor and just use the high-low.
On ground.
We're just making sure the other servo wasn't shot.
And what pin was it that
On
was?
3 volts.
Yep.
Let me just double check the pins.
So if I remember the last time I talked to Aaron, the servo was being used for like a spider that he was making.
Oh
yeah.
Yeah.
So we got ground is that's in the wrong one.
Yeah, so drop bears, for anyone that doesn't know, like they're kind of like koalas, but they're bigger, and they go high up on gum trees.
And 5, yes.
They tend to, like, what would you say that they do? Like they tend to
just
drop out
and
of the tree,
scratch,
right?
yeah.
And then they can scratch you like crazy. There's ways that we protect
There we
ourselves
go.
in Australia when
okay,
we're in the
now you go.
outback,
Now,
but
yeah, it was
it was the
my motor was fried. All right, so
Okay.
now it is working as opposed to. Let me get this on the camera.
Yep.
So we did have it right. It's just my servo was fried from my last
Well,
project.
let's
so
move this out. Yeah,
let's
there we
get this
go.
up going now. Now you'll see the servo. Where are we? Let's get this in the right view. There we go. You can see the servo spinning around. Right, so that's doing it's doing probably a 2/3 rotation. And the reason it's doing a 2/3 rotation at the moment is because what I'm doing is I've pinned it out to a digital pin, not an analog pin. So I'm not giving it a variance of how much I want it to rotate. All I'm doing is I'm giving it the full force of the 3 volts every 1.5 seconds. So it's basically taking that as an instruction to just do a full 3 volt spin. So my other, looks like I'm gonna have to throw that other one away, but essentially all we've done here, if I go back to, you want to bring up the code?
Yep.
Actually, I deleted what I was writing before because I've just pinned it into what we already had running. So if you bring
Well,
up
why
the
don't I
code-
bring up? Yeah, let me get this view right, and I can hold
you
that
want to hold
while
that?
you.
Yeah. All right. So what I've done is, obviously, as a few people have pointed out on the stream, so we've got there's 3 pins in a servo, right? So the 3 pins are power in, ground, and variance, or it's our gate. So what I mean by that is when we have power in, it's not actually powering the servo until the gate says turn, sends an on signal and sends the power through, right? So what we're doing there, yep, still going. So what I've done here is I've pinned the power into the 3 volts, obviously, so it will receive a full 3 volts when we tell it to go on. Then it will do obviously the ground is for the power going out again. Then, because we've plugged it into the same pin as the red flashing LED, it's now just getting the full 360, 3 volts through, so it'll do a full 360, not quite a 360 rotation.
Yep.
It looks like
Like 280.
almost 3/4.
Yeah.
So yeah, 280. So it's getting the full force of the 3 volts for 1.5 seconds and doing a 280 degree spin.
So how would you make it spin the other way, Aaron?
Spin the other way would be reverse
we just put it
polarity.
into America, right?
Yeah.
Like
So you reverse the polarity basically, but
my joke for everyone is that there's this common thing where toilets flush the opposite way around in the northern versus the southern
it's true.
hemisphere.
I just came back from
Yeah,
Seattle
yeah.
and I took a video.
That was
so-
proven on The Simpsons, I think.
Yeah, I think it was.
Swap the red and the black wire, and we should see that rotate the other way.
So that I don't know, because that will be it might be power and ground. So if we go ground into power and power out to ground,
our fire.
I don't think we would see it reverse because it's not reversing the polarity because the power goes into the power in, right?
Yeah.
All you've just done then is change the circuit. You've not actually reversed the polarity. Yes, you're sending power into the ground, but the circuit is not designed.
Unit, yeah, the servo circuit.
Yes, correct. So it's the yellow pin that we have to change on the analog pin to reverse the polarity. So if we swap that back again, but there you go. So you can see some live debugging of hardware as we go along. And if I get that running again, because it terminated.
Not looking too healthy. We've still got plenty of heat, so the battery is fully charged. I don't know how we're going to go with like getting it going again without some paper.
Reconnect. There we go. So we should get the spin.
There we go.
Yep. Yeah, we did get a spin running, and all we're doing here is it's pinned out to the pin 16. So pin 16 is all we have to program for in terms of a digital pin to say on and off. Now, if we wanted to go into one of the analog pins, then we actually have to give it an integer. So we're saying how much of the voltage we want it to send down the analog pin. I'm not sure actually. We'll have to check if these accept an analog input or if they're just digital input. I believe these are analog input because I was using these on my little spider. So I developed little hexapods, and then you can set basically to set the gate. So the gate is like how much a leg steps out. You need to set actually how much it's going to rotate instead of a full rotation every time. You say rotates 90 degrees and then 90 degrees back.
So let's now just alter that code to put in. We've got LED 16. Let's just call it servo.
So that's a digital pin,
motor.
but we need an analog pin.
We'll pick another one. Then we'll save that onto the device, replug it back into the fire, which I've managed to get going again.
Yep.
And by the end of the stream, we should have this fully deployed servo motor rotating piece by fire. So I guess what we could do is if that servo motor was connected to something, we could have our fire rotate.
Yep. How long do you reckon it'll keep running? Like 36 hours? 20 hours?
Well, I think
because it charges the battery when nothing's plugged into it, right?
There was a bunch of tests about running Raspberry Pis and certain batteries. It's surprising how long.
Because this is less than a zero, right? As well. Like, this is pretty.
The way they ran some of these tests was effectively writing to a file every 2 seconds or something like that. So just in an infinite loop, just constantly writing, or maybe it was writing the timeout to a file. And that was the file existed on the SD card. Then you just go and put it on the battery and let it go and run. So at some point in time, the device will just power itself off, and you can go back then and look at the last time that you wrote versus the first time, and you can tell how long it was set on for. And going between the Pi 0, the Pi 2, the wireless versions, all the way back to Pi 1 and Pi 4, it was surprising how long they would last. And this was on this specific battery that they were measuring, but it was a long time. Now, this is a chunky kind of battery, I guess. So I would expect, running maybe the servo motor would flatten a little bit, but if it wasn't running the servo motor and just running that LED, it would be a long time. Way back, I had the Pico running off a tiny little solar panel. And the tiny little solar panel, I know it wasn't providing the full 5 volts, so the LEDs were very, very dim. But it was running off extremely low voltage, so I would expect it to run for a very long time.
Yeah, well, I have seen people on zeros for a day or two.
It would probably
on a big battery. Yeah.
Even off this battery, it would probably last, a day. Maybe not running the servo motor, but definitely running the LED. It would.
So I'm not even getting servo value. Even if I do one, if it was pretending to be a digital pin, I'm pretty sure that's pin 35. If anyone else on the stream knows better, give me a analog pin. I'm pretty sure GP28 is an analog pin. That's ADC2.
We don't have much time. Maybe just put it on a digital pin and don't worry about it. And let's just burn it on. Deploy it onto the device, plug it back in, and see if we can get that going today.
Although the fire's just about. I think it's the wind. It's very windy. someone's given some example code that might help as well.
Oh
actually,
yeah,
if
what
you
do we
know.
got here? Machine
.pwm.
pin 15. Cool. Machine PWM machine pin 15.
Can give that a quick go.
Yeah, let's do that.
No, I think that there is flame in there. I think it's just yeah, there is a bit of flame. It is burning, but it's just not like roaring out of the top. So
I
it's
don't
still
need
got
to
power.
call machine for pin because I've called it out directly, but I can do PWM. So machine PWM, and that's pin 15, which is the one should be above. Should be the breakout 19. And then what else you got? That's it, just pin 15.
So even at the moment, why did it stop?
And then frequency. Yeah, thank you. So it's frequency, not value. Yeah, that's what. Frequency. And we're doing half. See, I'm used to working with different libraries like C, right? And so if I want to do 50%, it's a value of 0.5 instead of, so 1 is 100% and 0 is nil. So yeah, anyway, we're getting there. So we have we just need to change that to, line 6. Doesn't like line 6 because
I think what it shows is that building anything for one of these little devices is harder than you think. Like it's all well and good to say, "Oh, I'll make a light blink," but once you start doing something a little more complicated and you're mixing hardware plus software, the complexity sort of goes up. So even something really simple, and for us, like we're not doing this every
Thank
single
you.
day. You have to think about like, what are the pins, what are the numbers that I'm looking at, how do I
That's
interface
better.
with the library, what's the difference
Now we
between
need to
Python
run
and MicroPython.
this on this guy. So that should be pin 15, yeah? Let's just check the pin out. Oh no, that's pin 17. Pin 15 is on the other side.
Okay.
So are you sure that this is a digital analog pin? I didn't think that was an analog pin, pin 15. I thought analog pin was I thought pin 15 was a
Well, don't we need
so we need an analog pin, but I thought pin 15 was a digital pin. So we can try pin 26, GP26, which was if I've got or GP28, that's ADC2. These ADCs, I believe, are the analog pins. So 1, 2, 3, 4, 5, 6, 7. So if we go back to 7 over here, and I'll just change the code to be. You can see the camera. Change the code to be, that's 28. 28. Save that. Run that. Is our little servo doesn't want to move, does he?
No, he doesn't want to move.
Let's try, and instead of every second, let's just run it once and see if he runs around. Nope.
Yeah, we might need to just double check what the voltage is coming out at the other side there.
Float
Line
to
15,
int, yeah, so it has to be an
cool.
int.
It does have to be an int. Okay, so servo, pin 28. Has anyone found an analog pin or found a better, let's say, Pico?
This is the joy of doing it live.
Live
Yeah,
coding.
and I've
Yeah.
never programmed a Pico before, so this is fun. Here we go.
Maybe just go like
Yeah, these are your analog pins, so that's what I was right. 28, 27, 26 are all your analog pins. So the one that I've got it pinned into there is 28. That should be an analog pin, so that's correct. Power management on pin 28. then that gives us a frequency of 50. Let's bring that back up into every...
So is there some syntax error there?
No, that was from a previous...
That was from before?
Yeah. So that's the correct syntax. I'm not sure... I'll have to look into this because... no, I think what I've done wrong is... I've pulled out the... that should be...
You should have had that.
That should always be in constant. That's
Yep.
right. It's the other one. There we go.
There we go.
No. So that's
Nope.
our...
That's the old.
blinking,
That's
Yep.
this guy goes into this guy here. Doesn't want to work, but yeah. So what I did is I pulled out the power. So the power should have stayed, and pin 28 should be. Is it 7 on? 1, 2, 3, 4, 5, 6, 7. Yeah. So pin 28 is. It actually should be our switch on the servo, or our gate on the servo. So that now I would expect to be working. So I don't know why it's not working.
Well, let's debug this next time, but just before we go, let's eject the device. I'll plug it back in. We'll see if we can make the servo and the lights run off the battery. So switch your white wire,
So
or
we
your switch.
run the
Put it back on.
switch back onto the digital pin.
So pass me the USB. And that should just boot up again. Power that in.
This goes that. This goes over to the fire. Let's get the camera back on so I can see.
I will
Both of
take
it.
away
And
the
there we
screen.
have it. We've got the Pico. We've deployed some code which didn't work, but at the very least we've now wired in that servo motor, which is probably a little bit weak, which is why it didn't want to lift itself up. But
There we
you
go.
can see it's there running in that loop, just sitting there running over and over again, continually turning, and it's powered by fire. So I think, we'll have to think about some prizes to give away a Pico W, and maybe at some point once we set up a Pico W, we can install one of the AWS libraries on and then connect it, do something then into AWS next time. So this week was actually nothing to do with AWS.
Yeah, nothing.
It's setting up the groundwork for something that we want
So
to do.
Well, if we had a wireless
I do
one, we
actually
could,
have.
yeah.
Yeah, I was going to say I do have like a PiCom, which has a wireless hat
Yep.
Yep.
that we could actually do this exact same pin out on the PiCom using the Python, and then we can use the wireless to connect to the cloud, and we'll
And then do
send
a
some
stop-start
sensory data
Lambda or
up.
something,
Yeah,
I don't know, something
send
like
something
that.
up to a Lambda.
So
We'll make it a cloud relative project.
Yeah.
But
So-
today is fun. Hardware, just playing with hardware.
yeah. So yeah, thanks everybody for coming along. Brett, get in contact with us. We'll.
I think he's pinged me on
he's already
Twitter.
done
So
it?
yep.
Great. Yeah, thanks Aaron for being the hands-on coder. Hope you enjoyed it. Hope the sound was okay, given that we were all outside. We tried the best we could to get it set up and running. But thanks everybody, and we'll see you again same time next week.
Done. Thanks everyone. Bye.
Yeah.